A question. It's from June 2005's physics exam. So first question, when describing the photoelectric effect, a student writes the following. In order to emit photons from metal surface, incident electromagnetic radiation of wavelength greater than a certain threshold value must be used. So identify two important errors in this statement. So whenever we think about what the photoelectric effect actually is, we've got our metal, and then we've got our incident photons, and then we've got our liberated electrons from the metal. So the electrons are all sitting just below the metal, and then the incident photons, once they have a greater energy than the threshold energy, they'll be liberated. So what are our two important errors? So the first one is emit photons. So we're not actually emitting any photons. We already have the photons, and they're incident on the metal, and then the metal emits electrons. So that's error number one. And then the other error is that incident electromagnetic radiation of wavelength greater than a certain threshold value must be used. The threshold value is energy, so that's going to be phi, and that is a quantized value which is equal to h times f, which is Planck's constant times frequency. So our threshold value is in joules. It's not going to be anything to do with, well, it's something to do with wavelength, but it's not going to be in wavelength. Okay. So then we're going to go on to the sort of Malsey question, which is calculate the energy of a photon. So that's what we want. We want to have the energy of a photon of ultraviolet radiation of wavelength 250 nanometers. Okay, so a wavelength of 250 nanometers. If we think that our equation is E is equal to HF, and we have wavelength, we want that wavelength to be in terms of frequency, because we already know Planck's constant. So Planck's constant is H, and H is equal to 6.63 times 10 to the minus 34 joule seconds. Okay, so whenever we think about wavelength, the photons are a wave, and the wave equation is V is equal to F lambda. Because the photons are electromagnetic on the EM spectrum, it's going to be C is equal to F lambda. So we want to find F frequency, and we already have lambda, which is our wavelength. So if we do the speed of light divided by the wavelength, we will find our frequency. So we know that the speed of light, which is C, is equal to 3 times 10 to the 8 meters per second. So if I do 3 times 10 to the 8 divided by 250 nanometers, and nanometers is times 10 to the minus 9 meters, then I'll find the frequency. Let me just plug that into my calculator. So 3 times 10 to the 8 divided by 250 times 10 to the minus 9. So our frequency here is going to be equal to 1.2 times 10 to the 15. And that is hertz, or seconds to the minus 1. So whenever I plug that back into my initial equation, my energy equation, to calculate the energy of the photon, I know that the energy is equal to Planck's constant, which is 6.63 times 10 to the minus 34 times the frequency, which is 1.2 times 10 to the 15. If I do that in my calculator, I will get 7.96 times 10 to the minus 19 joules. So if I want to work that out in electron volts, then what I do is divide it by the value for 1 electron volt. So I know that an electron volt is equal to 1.6 times 10 to the minus 19 joules. So if I want to find my energy value in electron volts, and it will sometimes ask you for this, all you need to do is 7.96 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19. And the answer for that there is 4.9725 electron volts. So the three significant figures, 4.97 electron volts. Okay, so thinking about the question that we were asked